right, hi. Thank you for having me, even if virtually for now. Today I'll be talking to you about something called Counterdiabatic Optimized Local Driving, or COLD for short. This is work that was done at the University of Strathclyde along with my supervisor Andrew Daly and postdoc in our group Callum Duncan, as well as Anatoly Polkovnikov from Boston University. If you're interested in anything that you hear about today, the preprint is out on arXiv and is hopefully coming to a journal near you very, very soon. So please keep an eye out and feel free to visit along and ask me and find me and so on and so forth. And without further ado, the main thing we're going to be talking about today are adiabatic processes. Now, the main idea is that you take some Hamiltonian that is time-dependent according to some function lambda. So wherever you see lambda, that just means some time-dependent function. Insert your favorite time-dependent function in there. And the point is that it varies very slowly. Now, the reason we need to do it slowly is because, based on something called the adiabatic theorem, assuming you start in the eigenstate of the Hamiltonian at the initial time, so at t0, if you evolve slowly enough, according to this adiabatic evolution, you will end in the corresponding eigenstate of the Hamiltonian at the final time. So say you start in the ground state of Hamiltonian at time 0, you're going to end up in the ground state of the Hamiltonian at time at the final time. And you can see that in the picture on the right. Basically, say you start on the bottom left side with the thick red line, and then you move, you start to evolve. Assuming you have an adiabatic evolution, you're just going to follow that red line all the way to the end. You're going to stay in the eigenstate of this Hamiltonian. Now, adiabatic processes are very interesting and very useful. I feel like I have to mention this because there's something we're very interested in general as theory, in theory and experiment. They're useful for adiabatic quantum computations, optimization problems, other things like that, state preparation, any sort of quantum annealing, phase transitions. All of these things are captured by adiabatic processes. So we want to do them well, right? Now, there is a problem, which is adiabaticity inherently means infinitely slow times, which is basically impossible. You can't evolve infinitely slowly in practice. So what ends up happening is that you have to speed up this evolution, usually far more than infinitely slowly, because you have coherence times to worry about in your system, right? So you have to go quite fast indeed. But this speed up leads to losses, leads to transitions out of the eigenstate. So it kind of destroys the whole purpose of an adiabatic evolution. These losses basically translate to, if you start in the red thick line, at some point in the evolution, you might jump to the blue line, you end up in a completely different eigenstate. So that's bad. So what I'm really going to be telling you about is, well, what do we want? As I've sort of motivated before, we want adiabatic dynamics. We like them. But when do we want them? Well, we want them now. We want them as quickly as possible. But we also don't want these losses or transitions. So my talk today is going to be concerned with how do we achieve this? How do we speed up these dynamics and yet mitigate or minimize the losses associated with them? And we're going to do this using two main sort of crutches, not crutches per se, but two main fields of research. You've got shortcuts to adiabaticity and optimal control. And we're going to use a very particular method from shortcuts to adiabaticity called local counterdiabatic driving. So both of these contain many methodologies, and we're going to focus in on a few. And we're going to stick them in a pot, we're going to meld them all together, mush them up, boil them for a bit, and we're going to come out with something called counterdiabatic optimized local driving, or COLD, which is a method I will spend pretty much this entire talk presenting to you and explaining all of its components, and then I'll flash up a few results at the very end. So first off, we're going to start with counterdiabatic driving. So imagine that you have some system, it's time dependent, it's time dependent to Hamiltonian driving it, so you can always transform it to some moving frame, and in this moving frame, you're going to have this Hamiltonian, which will consist of some diagonal component and these off-diagonal terms, which are basically encompassed by something called the adiabatic gauge potential. Don't worry too much about it. That's just what I'm going to call it. And these off-diagonal terms are basically those responsible for the transitions, that we don't really want. So we want to mitigate these terms, basically. Now, in order to explain more intuitively what counterdiabatic driving is, we usually take the example of a waiter trying to carry a glass of water to a table. Now, as the waiter accelerates in order to get the glass of water to the table faster, he induces this fictitious force on the glass. The glass starts to wobble around. Worst case, it might even fall over. So what the waiter does is he basically tilts the whole tray with the glass in order to counteract the forces that are being induced by his acceleration, and thus stabilizes the glass, hopefully up until the point where he gets it to the table. Now, in counterdiabatic driving, we're basically interested in the exact same thing. We've got this sort of analogy of this fictitious force, the adiabatic gauge potential, and we will try to engineer a Hamiltonian that exactly counteracts these off-diagonal terms. So we're going to add some driving, add some external force that's going to push back against these off-diagonal terms. But that is not always possible. In fact, it's impossible for most systems of interest unless they're incredibly simple. So the adiabatic gauge potential may require sort of exponential fine-tuning throughout the evolution process. You need to know the entire system, all of its instantaneous eigenstates in order to characterize it fully. And these terms can be highly delocalized throughout the system. So to illustrate this, imagine that you have a spin chain. Now you start with a single spin. For this adiabatic gauge potential, which is generally imaginary for real Hamiltonians, might be just single local sigma y term. Now, if you add a second spin, well, you're going to have a single local sigma y term on each spin, plus all of the interaction terms between the spins that are also imaginary. Now, imagine adding a third spin. Well, you're going to have to add all the three body terms at this point in order to capture it fully. Now, we don't know what impact each of these terms have, but you have to consider all of them because a priori you're unsure which interactions you're going to need. Now, you can imagine that this gets very, very complicated very quickly the larger the system is. So you can't really implement this perfect counterdiabatic drive. So what you try to do, and what Anatoly Polkovnikov and his colleagues did, was to devise this approximate counterdiabatic drive. Remember that the waiter doesn't exactly know how each molecule of water in the glass moves. He just sort of generally approximately turns the tray in some particular direction to counteract most of the damage and to keep the glass just about stable. Well, that's kind of what we're going to try to do. So we're going to choose an ansatz for this adiabatic gauge potential, and there are ways to do this to sort of intuit what kind of operator basis you might need, and we'll perform some variational minimization. All of this is in the paper linked at the bottom. I'm not going to go into the details. To give you an idea of what this ansatz might look like, in our spin system, to first order, it would be just the local sigma y term. So we would just take an ansatz with some coefficient, which we're going to find through minimization, called alpha. And then to second order, you would, on top of that alpha, you would include all of the two body terms, for example. So that would be the second order local counterdiabatic drive. So this is kind of what local counterdiabatic driving is just an approximation of a perfect counterdiabatic drive. Now, the second component of our method is optimal control. This is much simpler to explain. You simply take a system that you're trying to evolve in time and you add some time-dependent control field or some control pulse to the system, and then based on some metrics, so be it the expectation value of some observable or the final fidelity of the state or the energy of the system, you optimize your parameters beta, which characterize this control field that you've added. So it can be any form of control field, anything that you're comfortable with. In this case, we use the final state fidelity, but obviously you can use others. So right now we've got all of our components. We start with some adiabatic protocol, some Hamiltonian that's time dependent. Remember this picture. We're going to add this control pulse to the Hamiltonian. So your control pulse of choice, it can be very local, it can be delocalized, whatever you want to do. And then on top of that, we're going to add a local counterdiabatic drive, which will now inherit this parameter dependence from the control pulse, because we're basically trying to now counterdiabatically drive whatever Hamiltonian that is composed of our original and our control pulse. And we're going to optimize these parameters now, not just for the Hamiltonian and the control pulse, but for the Hamiltonian control pulse and the local counterdiabatic drive. And just to flag up a very quick result, this is just for a spin chain, 5 spins. You can see how the local counterdiabatic drive really doesn't perform well. The blue dots are simply optimal control. And then we see that at very short time, so on the bottom there's the driving time, at very, very short times, the fidelity of the final state for driving across some transition is very, very high. And so that's on the left side. On the right, we just include this method called CRAB from optimal control, which is a very popular method of optimal control. We show that we can combine it with that as well and get very good results at short driving times. So in summary, we have a new method called COLD for speeding up adiabatic processes. We're also working on frustrated spins, for which you have some very nice results at the moment, so keep an eye out for that. And there's this method opens up very many new avenues to explore. I hope you've enjoyed this. If you have any questions, feel free to reach out. Thank you very much.